We are recording. We are live, people. Okay. So look, the first thing you should think about, before even jumping any calculus at all, is the domain. Let's think about the domain of this thing. And domain is really only three things. You can't divide by 0. You can't log anything that's 0 or less. And you can't square root anything that's less than 0. Okay? There's no logs. There's no division. And the only roots we have are cubed roots. Y'all see that? Because we have to the third, the 1, 5/3, 4/3, whatever fraction. So they're cubed roots. So domain of this are real numbers. Okay? Okay. Second thing we should think about is like vertical asymptotes, things like that. But that's only by dividing by 0 or log. So that's not here either. Okay? And last thing you should think about, just kind of quickly, real quick, before you start getting work, is the end behavior of this thing. All right? Now, sometimes it's easy with like horizontal asymptotes and things like that. This one's a little bit weird, but let's think about this. If x gets real big, what's 2x to the 5/3 going to do? It's going to get big. It's going to get big. Minus, what's 5x to the 4/3 going to do? It's going to get big, but less big. And as x gets bigger and bigger and bigger, the difference between them is going to grow. Where's this graph going to go as x gets huge? Infinity. So we should find out at the end of our first derivative number line that the interval is positive. Okay? That should definitely happen. Okay? Now, whether it's concave up or concave down, it's a little hard to tell sometimes. But we at least know the first derivative should be positive at the end. Okay? Also, if we were to think about plugging in gigantic negative numbers, what kind of number is this going to be? It says 5th power, then cube root that. It's going to be a big negative number, right? What kind of number is this going to be? To the 4th, then cube root it. It's positive. So we have a negative number minus a positive number, and they're getting bigger. Where's that going to go? Negative infinity. So we should find on this side of my derivative that it should be increasing there as well. I know I'm drawing it going down because that's from right to left, but from left to right, the graph will be going up. Does that make sense? Okay, that doesn't tell us a ton, but at least lets us know if our first derivative is giving us the right information here. Okay? Couple of things you can do if you wanted to is try to find the zeros of this stuff and everything, but you can probably just jump right in and start doing this, okay? So, let's derive this thing. The derivative of this thing is not crazy difficult, right? The first derivative is 10/3 x to the 2/3 minus 20/3 x to the 1/3. Right? Right. And we need to know, where is that dumb thing going to be 0 or undefined? Well, it doesn't have any fraction part to it at all, right? The x, y's, there's no negative exponents or anything. So it's not going to be undefined. Okay? But to tell where it's 0, we got to factor it. So, what can we factor out of there? Ooh, 10/3. You guys sound so excited. 10/3 x to the 1/3. Yes. And that's going to leave us with x to the 1/3 here minus 2. And once it's factored, you can see what makes it 0. 10/3 is never 0. X to the 1/3 will be 0 when x equals 0. And x to the 1/3 minus 2 will be 0 when x equals 8. You can write that on solve it if you want somewhere, but it's just 8. So we're going to make a number line. And on that number line, we're going to put 0 and 8. And next to my number line, I'm going to write dy dx or just y prime or whatever. Because we're testing the first derivative, and I want to make that very clear to myself so when I look at it later on, I'm not confused about what this number line tells me. Okay? We're going to take a negative number, doesn't matter, negative, I don't know, 8, negative 10, negative 1, doesn't matter what it is. We're going to plug it in. When you do that, when you plug in a negative number here, 10/3 is positive, that's not changing. A negative number to the 1/3, negative. A negative number to the 1/3 minus 2, negative. Okay, so it's positive, which means all the way over here, our graph is increasing, which we suspected because we checked out the end behavior before we even got into this. So, okay? All right. Also, just going through here, you can see that none of the roots that we have here are double roots. 0 was a root because of this x to the 1/3. If that was to the 2/3, that'd be a double root. Okay, but it's not. It's to the 1/3. Okay, so it should change sign at 0. And 8 came from the x to the 1/3 minus 2 here. That's not a double root. So we should see this thing change sign. But you should still check just to be sure. So plug 1 in. You're going to get a positive 10/3. 1 to the 1/3 is positive. and 1 to the 1/3 minus 2 is negative. So the graph is decreasing here. And if you plug in anything bigger than 8, you're going to get a positive, so the graph is increasing. So we have a graph that goes up, down, up. Cool. A lot of times with these weird fraction exponents, you get like corners and stuff too. I don't know if that's going to happen in this case. Actually, it's not, because the derivative is never undefined. It's just 0. Cool. But with these weird fraction exponents, sometimes you get the derivative undefined, and that means there's like a weird kind of cusp or corner point. Okay? All right, so anyway, we got to drive this thing again. We got to find the second derivative. So I'm going to do it right over here. That's d squared y over dx squared. And we have two versions of our derivative here. They're both the same, but I'm going to choose the one that's easier to derive, and that's the one that's separated, not factored. I'm going to derive that one. Okay? So to derive that, we just got to do the power rule. That's going to give me 20/9 x to the negative 1/3. So I'm going to put that right down the denominator. Minus 20/9 x to the negative 2/3. So I'm going to put that right down in the denominator. Okay? And that's the second derivative. That was pretty easy. We just got to put it all together and find out what makes it 0 or undefined. Right away, I can see that 0 is going to make this thing undefined, right? Because we got those denominators down there. But I told you too, like, you want to get a common denominator is how you're going to handle fractions. So our common denominator here is going to be 9x to the 2/3. Okay? That's the highest exponent, is 2/3. Which means I need to multiply this fraction on the left here by x to the 1/3 over x to the 1/3. And that's going to give me 20x to the 1/3 over 9x to the 2/3 minus 20 over 9 x to the 2/3. And since we have a common denominator, we can piece this all together. Our second derivative, I'm going to draw a big line here to separate my first derivative stuff. Our second derivative is going to be 20x to the 1/3 minus 20 over 9x to the 2/3. And you can factor a 20 out of the numerator here, but I hope you guys can see right from this point that 1 is what's going to make that 0 up top there. Okay, so 1 is going to my number line, as is 0, because that makes the denominator 0. And right next to my number line, I'm going to write d squared y over dx squared, so I remember I'm testing the second derivative here. Cool. If I plug in a really big negative number, or any negative number really, -1, whatever, the top is going to be a negative thing, right? Negative 20 minus 20. And the denominator, because it's to the 2/3, is positive. So we have a negative over a positive, which is negative, which means my graph will be concave down there. All right? If we plug in a number, so this is weird to have like a weird interval 0 to 1, but just plug in a half. It might make it easier if we were to factor this thing here. I wasn't going to because I was trying to be lazy, but you're going to have this. Yeah, if you're having trouble plugging in, factoring it first makes it a little bit simpler. If I plug a half in, or even if you're unsure, plug in something real close to 0, 0.00001. Okay, a super tiny number close to 0. All right? The 20 is going to be a positive thing. 0.0001 to the 1/3 is a very small number. Minus 1 is negative. And on the bottom, 0.001 squared is going to be a positive thing. Okay? So we have positive, negative. It's negative. And if you were thinking about our rules in the first place, why should we expect it to go negative and then negative again? Minwoo?
Because the 9x to the 2/3.
Yeah. Yep. 0 came from that x to the 2/3. That's a double root. Or double asymptote, really. It's down the bottom, right? So it's not really called a double root per se. But it's a double 0 of the denominator. That's why it doesn't change sign there. Okay? And if you plug in anything bigger than 1, you're going to get positive. What's up, man?
Wait, so regardless of whatever happens, like if anything at the bottom or the top, like if it's to anything to the 2 or 4 or anything even, then you have to double root it?
Yeah. Yeah. Okay, you don't have to. Again, you can always test your intervals, but it should work out like that. Okay, it doesn't matter what the root is. Cool. It matters what the power is. Like the cube down there isn't going to change it. It's the squared that does it. The 2 up top. Okay. So we have concave down here, and we have concave up here. So, and all I'm going to do is have you guys list this out. Okay, does everybody feel like they can do that right now? Like, let's just do it. Increasing is going to be from negative infinity to 0, union with, what, 8 to infinity? Decreasing is going to be from 0 to 8, which means we have a relative max, where? At 0. And if you plug 0 in back to the original, because we want to know the y value of the point, you just get 0 again. There's a relative min at 8. Okay, what? Plugging in 8, a relative min. You imagine being a relative to min? Cool. Got him. Okay, anyway. Yo, plugging in 8 is not too bad, look. Because these are just cubed roots here, okay? They're just cubed roots. So, yeah, when you plug in 8 to that, let's think about this. I'm drawing this over here. You're going to get 2. The cubed root of 8 is 2. So that becomes 2 to the 5th power. That's what's going on there, okay? Minus 5. The cubed root of 8 is 2. So you're going to get 2 to the 4th power. I know, right? It works out relatively nice, right? Okay. It doesn't always work like that, but this one works out kind of nice. So we can actually find this, right? 2 to the 5th is 32 times 2 is 64. And 2 to the 4th is 16 times 5 is 80? Yeah. And 64, take away 80 is negative 16. That wasn't too bad.
Wait, don't you have to do the powers first? Like, you have to do 8 to
No, so roots and powers happen, you can do either one first. So if you can do that root first, do the root first. Yeah, much easier. Okay? And that's happening. Let's just discuss. Ready? What was it? It was 8 to the 5/3, right? That's the same thing as 8. It has to do with the associative property of multiplication. That's the same thing as 8 to the 5th to the 1/3. But it's also the same thing as 8 to the 1/3 to the 5th. It doesn't matter which one you multiply in first, okay? That's why that happens. So yeah, if you can take the root first, do the root first. And then we're going to have our concavity stuff. So we have concave down from negative infinity to 0, union with 0 to 1. We're going to split them apart because it's not concave down at 0. The second derivative is undefined there. And our definition for concave down is that the second derivative is negative. Okay, not undefined. And it's concave up from 1 to infinity, which means we have an inflection point at 1. And if you plug 1 in, you get 2 minus 5, negative 3. Is it okay? What's wrong? Why are you making faces?